So, hi everyone, and thanks for joining. We're going to talk about data drift, which is one of the most common issues and also one of the more tricky ones we deal with when deploying machine learning models to production. And it becomes even more tricky when dealing with unstructured data, such as text, and this is exactly what we're going to dive into. So, a short outline, and then I'll present on myself as well. So we're gonna do a short intro just to align about what is drift, how can we detect it, how do we do so on unstructured data. We're gonna talk about concepts such as metadata, properties, embeddings, and then we're gonna also show a demo how we can kind of inspect and understand drift using properties and embeddings on textual data. So short intro about myself. My name is Shir Cherev. My background is in research, starting in Tabular Excellence Program, which is a IDF program for elite technological leadership with about like 50 elite graduates. And then we go on into various tech positions inside the IDF. Personally, I started with quite a low-level cyber background and then transitioned into data science, where I was lucky to work on quite interesting stuff, including leading research for anti-terror related use cases. And that's also where I saw the immense value in machine learning models and how these, well, at that time was relatively new techniques. Now I would say more established techniques can really give a lot of value and kind of get new stuff that we weren't able to do manually on one hand, but on the other hand, they also come with a lot of challenges. So that was a main reason for founding DeepChecks, which I'm the CTO of. And in DeepChecks, we work in continuous validation for AI, which means basically being able to help detect and then also mitigate and solve problems in machine learning models or AI, because it includes also LLMs, from the research phase through the kind of pre-production, like during CI/CD, and also during production when monitoring them. So I'll say a few words later. And in that context, obviously, we do have a kind of a lot of insights and are dealing deeply with drift, and we're going to share quite a bit of that now. And in DeepChecks also we have an open source package, which actually the demo is going to use. So you'll see that in action as well, and I encourage you to try it yourself. Except from that, personally, I love training in general. So not only models. You may see me if you're in Tel Aviv or other places in the world, like soon in Berlin, running and doing lots of types of sports, kite surfing, skiing, and kind of traveling around on my electrical or non-electrical unicycle. So starting with a short kind of intro on drift, I guess most of you are familiar with, but just to align a bit the terms themselves. So in general, drift is a situation when the data, labels, or their joint distribution changes over time. If we broadly categorize drift, I'd say that there are two main categories. One is data drift and concept drift. So an example to exemplify the difference between them is data drift is a general kind of change in the let's say a distribution of the data or the input features. So for example, let's say we're now in a town. I mentioned Berlin. So let's say Berlin now opened a new university. And suddenly, many more students are coming to the university, changing the characteristics of people that are currently looking for apartment. If we have a model for house price predictions, what changed now is that there are many more of a certain, whether it's a certain demography, like specific ages, types of houses they're looking for, or maybe the location of the houses, like near the university. So there would be a drift in the input distribution of like the feature space of the model, which may or may not have impact on the performance. It really depends, like on the specifics of let's say now there are again many more students. So did the model in the first place behave quite accurately on that demographic? And if it did, then it may even not change the performance itself. If on the other hand it was like a smaller space and now the performance was worse, it may also deteriorate in general. So that's like the general notion of data drift. Concept drift is actually where the labels distribution changes, like its distribution changes in relation to the same input data. So let's look at the same example of a model for predicting house prices. let's say that now the population grew drastically, or it's a huge university and lots of students came in, and many more people are looking for apartments. So there's much more demand, but the supply doesn't rise as quickly, right? It takes time to build new buildings. Then it may be that for the exact same input features, or the exact same, again, search parameters, the prices are now much higher. So the real label is actually much higher, which would require basically retraining the model to relearn the new relation between the demographics of the input data and how they affect the label. So let's look at maybe more kind of domain related example. So for NLP, if we look at search terms on the word, search frequency on the word Twitter over time, we can see here, this is a graph from Google Trends. So what we see here is over time, and we can see some change around a specific time. So this is the frequency of searching Twitter. So we can see, first of all, a data drift, right? Because in on certain time frame, the term was much more popular. And also, if we look at the actual context, or in this case, the sentiment of the search, we understand there was also a concept drift here, because while the term Twitter hiring, or let's say in a positive sentiment, rose a bit, Twitter firing, and we remember that happening a year or so ago, was much more popular. So again, here, if we would try to predict what the people were searching for, and we see only the word Twitter, then kind of the label is changing. Or again, if we predict, let's say, the sentiment. Now, this may not this may also have additional aspects. Like if we look also on a geographical scale, we can see that in certain demographies, it was much more popular to search for Twitter firing, while in others it was much more popular Twitter hiring. So it really depends also on the subspace of where we actually look at these changes. So when we look out for drift, as you probably understood, we're comparing between distributions, right? So whether it's over time or between X and Y, and what do we actually compare to? So this actually changes really in relation to which type of model we're actually talking to. So classic NLP is what I define, or what we would define everything before the, let's say, transformation of LLMs, which maybe now seems quite far away, but let's say up to a few years ago. And then what we had is we would train our own model. And one thing that we want, especially let's say pre-production, is to compare our test data set, or the data set that we an example from the inference data that we're now going to deal with, to the training data. And then we have a sense of, is the data that the model is going to see in production, is it representative or not? So that's when training. For LLMs, some would maybe say that, okay, there is no training data, right? There is obviously, but it's all of the internet. So maybe if we do some fine tuning, we can also use those aspects. But let's say if we're talking about a generalized LLM or foundation models, we would want to, in order to understand, is our performance, or is the data behaving still the same as we expect it to, a reasonable thing to compare it to is the data set that we used in order to evaluate it, especially if it's broad enough. And if not, we do recommend having a relatively broad data set. And we can see, again, the notion changes a bit in LLMs, but there is still something that we can compare it to in order to understand, does it generally behave the same or not? And in production, one thing is, and this is relevant for both cases, is if the same models in production over time, we can also compare to, let's say we know the previous day's data, whether it's only data or we may have also the performance. So we can compare today's with, let's say, the first week in production, or today with yesterday, and so forth. So that's what should we compare to what? And okay, so we understood that we want to compare things, we want to see the distributions, but how do we actually detect drift? So when we look at univariate drift for, let's say, simple numbers in this case, well, we have quite a lot of statistical tests or metrics that we can essentially plug in the two distributions of what we have, or a subsample of it, and get a number out of it. So if we run a Kolmogorov-Smirnov or earth movers distance for numeric data, and also similar metrics. So we have for categorical, like these are just a few examples. You can see also in the open source where we have drift metrics, then they're implemented. So and we can decide a certain threshold for that number, that if the drift score is above X, then okay, we would consider this as very drifted. So here we're talking about univariate, so like on one feature, and we get one number. But what if we have a multivariate drift, right? So what if like the drift isn't in a single thing, like the location where let's say of the apartment in the example we gave before, or the age, but rather some combination of them. So we would want to have a way to detect a multivariate drift. And now I'll explain a bit how a domain classifier works, which is a technique we find very useful for detecting and also understanding in which specific features the drift happens. So what we do is we train a new model to differentiate between the two data sets. So what does that mean? Let's say we have a training data set, or well, not a training. We have let's say data set 1 and data set 2. Okay, before we said it really depends what we compare to, whether it's previous production data or whether it's let's say test data and train data. So these are the two data sets that we want to know, are they drifted one in relation to the other? So now we're going to train a model that is for detecting from which data set each sample came. Okay, so we have like the purple data set called the data set 1, and the second data set 2, and we add the relevant label. And we build just a new, like we build a merged data set to do a train test split on this new merged data set and try to see, can we differentiate? So we do a train test split and we train a model. Let's say it can be basically any model, let's say XGBoost or some tree-based classifier. It's nice if we have a good feature importance that we can then use. And then we can see, does the model that we trained, is it able to discern between the train and test that it was given? Okay, because if it did we check out its performance. So if it did a good job in being able to distinguish between the train and test, or in this case, it's if it did a good job in distinguishing between data set 1 and data set 2, essentially being able to understand from which original data set they each came, it means that there was a high drift, right? Because the model was able to distinguish between them. And well, how do we know from which features this high drift came? So we can inspect the domain classifier's feature importance, understanding, okay, which features did it use to actually differentiate between them? And these are the relevant drifted features. So that's a nice and a useful way to detect a multivariate drift, and it's also implemented in our open source and can be used. So we mentioned how to find drift in structured data. So when we have like numbers and we wanna like know, have they changed? But what happens when we have unstructured data, right? It can be a text or audio or vision, and how do we even like know if it changed or not, or what does it mean? So in order to be able to actually inspect the data and group it in some way, be able to see, was there a significant change? We want to transform it into some numeric representation, whether it's a number, a vector, or a category. So we have a few ways which we find useful to do so. So I'll mention them, give a few examples, and then we'll see it in action. So the leading ways we see is metadata, properties, and embeddings. I'll say a few sentences about each. So metadata is any additional information which is external that describes each of the samples. It can be things like what is the source of that sample, when it was created, when it was published, or where it was published, demographic data, location, really anything that comes with each sample. It can also be manually labeled. And well, a great something very good is this is very relevant for if we want to like group according to various demographics or things that really describe. It can be a very useful way to kind of understand some additional data. But a disadvantage of this is that it doesn't actually, it doesn't represent the sample itself, right? It doesn't relate. It doesn't relate to anything that is really content related, and that may be somewhat problematic when we want to really understand like what's happening there. Another example was another way to make this into structured data is properties. Properties really call any information that can be derived from the text. So we calculate this kind of per sample. And just to give a few examples, well, properties can be technical, things like length, characters, kind of limited TF-IDF encodings, which we can calculate. They can be linguistic, like language, nouns, anything really describing the text itself, or also domain-specific, whether it's the topic that it's talking about, sentiment, or really anything you extract from the text or calculate about it. Now, a big advantage in properties is that they really describe the text, so they're very explainable. And if, for example, you found a drift in a specific property, then that would be very informative when you try to understand what happened or how can you change it or improve it and really research it. While the downside is that drift doesn't necessarily behave according to the properties, right? The fact that we extracted a certain property doesn't mean that the text may be, for example, drifted, but maybe not in that specific property. So that's why you really need a wide plethora of properties in order to be able to see if they're interesting and where. And another common way to basically extract a vector representation from unstructured data is embeddings. Embeddings is really it's a group of things. So there are various techniques to extract embeddings, which are essentially, again, vector representations. A common way to extract them is using internal layers of neural network models. Today, with common LLMs, we have quite a lot of common embedding APIs, such as in the demo, you'll see the OpenAI ADA embedding, but it can be of a model that you trained. It can be like you trained it only for that purpose, or really of generalized model, like models like the one I mentioned. And also embeddings can be quite high in dimension. So many times you would want to also use the vectors after dimension reduction. Good embeddings would be embeddings that similar samples or that have some similarity or some representation between them are close to each other. So that they have close distance, and that obviously has the advantage of the fact that if there is now a change, so we would expect kind of these things to move away from each other. So that's a good advantage of the embeddings, is that it's easier, or it's likely to be able to find some change in topics, so forth, by finding a kind of change in the distances. So really, like we did before. While the disadvantage is that it's really not that explainable, because okay, so now the embeddings changed, but what does it mean, or where did it come from? And that's why also a combination, which we'll see soon, of properties along with embeddings can be very useful. So kind of summing up, we saw metadata, which is accurate. We can segment about it. It's also not always available, because it's really, if you supplied it or if you have it, then it's there, and it doesn't describe the text or the content itself. Properties, which are less accurate because they don't necessarily capture the content itself, but they can really be informative and explainable for finding drift and outliers, and they describe the text. And embeddings, which, while accurate, they have really a low explainability. So now let's see it in action. So we're going to use here the DeepChecks open source. In a second, I'll scroll up to the top. I'll apologize in advance that I ran it just before, because there are a few cells that take like a minute or two, and I didn't want us to wait, but we'll go over it together. So here we just download the data, so I'm skipping this part. We're creating a text data object, which is just an object that that has the data, like the training text and also the labels together along with the task type. So we're creating a text data both for the train and the test. And just to say a few words about the text itself. So what we have is news articles, AG news articles. That's the data set, and they have a label for which section they are relevant. So it's like business, science and tech, sports, and so forth. And here we're going to, for the properties, we can either calculate them themselves, or we can also like save them and or load additional properties. So in this case, we're setting kind of pre-saved properties. And we can see them here, things like length, language, formality, and so forth. And you can also use, in this case, again, we're using this is all from DeepCheck, so we also have a built-in kind of function if you want to just calculate properties. You can also add your own properties, which may like domain-specific properties. And same for embeddings. So we're downloading them here, just giving the label map, and we're going to train like a simple model, okay, just so we have a sense of we're going to inspect it, we're going to see the change and see how this affects the performance. So we're, in this case, just training a simple XGBoost in order to classify from which category is each of the samples. And so we have now a model which we trained and predicted both for train and test. And we're going to run a few checks. So first thing is we're going to find a data drift using the properties. And in this case, so we ran the property drift check, which calculates or takes, in this case, the saved properties and sees if any of them are drifted. So in this case, we can see that between the train, so this is the test and this is the train, and we can see that the formality of the train is much higher than the formality of the test. Let's see any more properties that are drifted. Okay, so text length, there's a slight drift for the train. Okay, so this is one thing. So we understand there is some change, but we still don't know how and if this affects performance. If we look now at the embeddings themselves, so as you saw before, we loaded them, and now we're running the text embedding drift. So each check in DeepCheck takes like a train and test. Well, depends. Some take also a model or only one of the data sets, but in this case, the drift checks all take train and test. And here we can see some visualization of the embeddings and their distribution in 2 dimensions. So if we have a look here, we can see that. So this is the train test. Okay, you can see their according labels. And what we did is we clustered them, like we ran a clustering algorithm and tried to extract the topics in a not supervised manner. Okay, so we just took the embeddings, ran a clustering, and then tried to extract, in this case, using OpenAI, but there's really quite a lot of techniques to try to efficiently extract the topics. If we just due to time restrictions, I'm not going into the specific technique, but in this case, it's quite a simple prompt in which we send like many of the samples and try to find, okay, what is the common topic for them. So if we have a look here, we can see that in this area and in this area, there's much more test samples than train, while in this area, there's much more train than test. And if we have a look here, so in this case, we also have the labels, okay? But also without the labels, we can see that in this area, the topic is sport events. And by the way, the label is also sports. And also in this area, we have sports, okay? Or again, the topic that we did in an unsupervised manner is sport events. So we understand that we have much more sport in test than in train. And let's have a look at this area. So here we can see that the topic is airline industry, or where here again, we have already the label, which is business. So we see that there are some topics that are much more popular just in one of the data sets. And let's see how this affects performance, and does it affect performance? So if we run the train test performance, we can see that in this case, let's have a look at the recall. So the recall on sports is much lower in general. And that does relate to the fact that we saw here that in this case, remember we saw here, so tests. So in the test data, we have much more sport-related stuff than in the train data, which makes sense that our model really missed them in the sports. And let's have a look from another kind of angle. This is the segments performance test, which if we look here where we segment, let's see how again, here we have already the labels. So the performance is actually much lower in areas of lower formality, which also makes sense, kind of understanding our what we saw before, because sports events were actually much more popular sports was more popular in the test, and business was more popular, just as a few examples, in the train. And it means that the level of formality really changed between the train and test, so because there are much more of one type in the train, and the model performed better on those. And then in the test, we see that on the lower formality, like sports, the performance was actually much worse. So just going back kind of, so we saw the drift, we saw how to understand. So what can we actually do with it? Well, first of all, what we should do, or what we recommend, is really to kind of check for drift throughout the process, like during testing, CI, production, and also save it, whether locally or in various tools, during experimentation and during monitoring. But what should we do with it? Have we, when we find it? So, well, first thing we can do to mitigate drift is really retrain the model, if it's a model we trained, or change the prompt, let's say if it's an LLM-based app. But we don't necessarily have the labels coming in time, right? So if we have, for example, access to the production data, we can see that there is some drift, but we don't yet have labels in order to act accordingly or to really improve the performance. So one thing we can do is to try to adapt the training data, if it's a model we trained, accordingly, whether it's to change a bit like the pre-processing, remove some features or samples, or add synthetic samples, which can be generated in various techniques. Or we can also build a model that takes into account the drift. So like way more specific training samples that are like more presented. So in the example we saw before, we would want to kind of put more emphasis on, in this case, the sports related samples, again, either by adding synthetic samples or by weighing them higher. Or let's say if we're in an LLM app and what we do is mainly prompt engineering, or kind of let's say improving our information retrieval, then just to make sure to modify such that it behaves better on those specific topics or on those specific areas, and really accordingly kind of adapt our evaluation metrics so it encompasses the production distribution and not only the training distribution, which would mitigate for that drift. And well, in both cases, we do need to actually know what's happening in the production, because obviously if we don't monitor it or don't see the change, then we won't be able to adapt and fix it accordingly. So we talked in general about drift, about how to find it, univariate, multivariate, and how to use how to transform unstructured data, whether it's using metadata, properties, embeddings. We saw some pros and cons in each of these techniques, and also how to put them together, while in this case, what we saw was a drift that we detected using the embeddings technique, but understood using properties. And just a few sentences about deep checks. So the demo you saw was all from our open source package, and we also have open source and a commercial offering for the areas of CI/CD and production. And you can scan here for more details, or to contact me if you'd like, if you have also any questions that we won't have time for now, or for any additional details. And I really want to thank a lot both the open source community for helping us and contributing and giving us feedback, and also, of course, DeepCheck's development and algorithmic team for doing a great job in implementing these cool stuff. And well, if you like what we do, then give us a star, and I'll be happy to hear any feedback and questions, of course. Thank you.
As today's session comes to a close, I want to say thank you to all of our speakers and all of you for shedding light on the most recent breakthroughs in AI. I would like to thank each one of you for your engaging questions and for sharing your experiences. It's evident from our discussions that open source efforts play a pivotal role in applying NLP and LLM techniques in practice. The range of tools and models presented today, tailored to tackle real-world business needs, is truly inspiring. The accomplishments of the open source AI community in 2023 have definitely been impressive, and by all accounts, we are just getting started. We reconvene tomorrow at noon Eastern Time for Day 2 of the NLP Summit 2023, with a spotlight on the role of NLP and LLMs in healthcare. We invite you to rejoin and be part of this ongoing discussion. Wishing you a pleasant evening and looking forward to our discussions tomorrow.